Hello, calculus students. Welcome to your online lesson. Today we're going to be talking about something known as conditional probability. And we will find conditional probability using tree diagrams, tables, and Venn diagrams. We'll know we're successful when we can solve IB level problems involving conditional probability. All right. We talked just briefly about conditional probability when we had Venn diagrams, but there's a formula for conditional probability, which we want to get in our notes right here. It's also in our formula packet. As we know, when we see a P here, that stands for probability. We have events A and B, and this line here means given. Given is the key word for conditional probability. And what does given mean? It means that we know something happened, or it's known that. So the probability of A knowing that B occurred, or the probability of A given B is how we'd read this first part of the statement before the equal sign. And then from that point on, we take the probability of A and B. Remember, probability is a number. Every time we see a P, that's a single value. So we find that one number between 0 and 1 that represents the probability of A intersect B. And then we divide by the probability of B. So it's a division problem. And that's how we do conditional probability. You'll mostly only use this formula when dealing with tree diagrams or when dealing with abstract problems just involving formulas. You won't need this formula for Venn diagrams usually, and you won't need this formula for tables. We're going to take a look at a few problems now involving really all those things. So let's start with a table. In survey, 100 students were asked, do you prefer to watch television or play sport? Of the 46 boys in the survey, 33 said they chose sport, while 29 girls made this choice. And we can see those numbers here and here. By completing this table or otherwise, find the probability of A and B. So if you want to pause the video now and see if you can fill out this table on your own, it's a little bit of a puzzle. But the first thing I would do is we know the total is 100. We know there's 46 boys, and so that means that we must have 54 girls. If there's 54 girls that liked sport, then we can subtract the 54 and the 29 that we have here, and we're going to be left with 25. And then we can do the same thing for boys. We have a total of 46. We take away the sport, and we're left with television, which would be 13. Now we can add up all the people who liked television, and we get 38. And we can add up all the people who like sport, and we would get 62. Now that we have that, we can actually do some probabilities. So the first probability, we want to find the probability a selected student at random prefers to watch television. Oh, okay, well, how many people like television? That's what we're looking for. That's our desired outcome, 38 out of our grand total of 100. And that's regular old probability. Now for part B, we see this word given, which means conditional probability. A student prefers to watch television given that the student is a boy. Whenever we have the word given, that becomes your new universe, your new total. So we were given that it's a boy. Start with that. So in our fraction, how many boys did we have? Well, 46. So out of those 46 boys now, how many prefer to watch television? And there were 13 boys of the 46 total that preferred to watch television. So that's a case of conditional probability. Condition means there's a condition given that we're just looking at the male students, and then of those, we have a certain portion that want to watch television. So when we deal with conditional probability on a table, it essentially shrinks our universe, makes our denominator a little bit smaller. And we'll see that on the Venn diagram example as well. All right, let's take a look at another example. So for this one, we have a Venn diagram. Once again, with a Venn diagram, you usually do not need to use the formula. We have a school of 88 boys. That's already been shown on our universe here. 32 students study economics, also shown. 28 study history. 39 do not study either, and we can see that there. This information is represented on the following Venn diagram. Calculate the values of A, B, and C. Well, we know that A plus B plus C plus the 39 have to add up to my universe, which is 88. I also know that A plus B right here is all part of the economics group, and they add up to 32. So now I'm down to one variable of C. I can combine my like terms, 32 and 39, which gives me 71 plus C equals 88. And so we get C equals 17, I believe. So I put that here. Now I can take the total of my history students, which was 28, subtract the 17 from that, which leaves me 11 here in the middle group. 11 plus 17, again, adds up to be 28. And now I can take this 11 and subtract it from the 32 over here with the economics, which gives me 21. If I add the 21, the 11, the 17, and the 39, they should all add up to 88 again. So the values of A, B, and C, A is 21, B is 11, C is 17. A lot of times with these IB questions, you get so focused on the math that then you forget to actually answer the question. Part B, a student is selected at random. Calculate the probability that he studies both economics and history. Well, the both is this intersecting sort of American football-shaped region, which is 11, and then our universe is 88. For part B double I see the word given. So that must be conditional probability. That means we're not looking at the whole picture anymore. We're only looking at what's given. And we're given economics. How many students study economics? Only these 32. So I'm only going to look at those 32. Don't look at the 39 outside the group. Don't look at the 17 who just study history. Only look at the 32 students who study economics. Now, of those, calculate the probability they do not study history. So a way you can do that is sort of cover up the whole history circle, which would include the 11 in the center, and then you're just left with 21 students. 21 that study history, given that they study, that do not study history, given that they study economics. Just remember, when we see the word given on a table or a Venn diagram, you're going to shrink your universe, not look at the whole thing. And I always write that denominator down first. Our last example is going to be arguably the most challenging one. I'll leave myself a little bit of room. I'm going to do probably parts 1 and 2 of this and leave part 3 for you to take a look at on your own. It says bin A contains 3 red and 2 white tickets. Bin B contains 4 red and 1 white ticket. A die with 4 faces marked A and 2 faces marked B is rolled. We're then going to select a ticket from the bin, either A or B. We want to determine that the probability is red, determine that the ticket was chosen from B given it's red, so on and so forth. Well, the first thing we need to start with is actually our a diagram of some sorts. And where we're pulling out tickets and rolling dice and things like that, that's a very typical tree diagram problem. Lots of actions. It's usually when it's categories that we use the Venn diagrams, actions we use the tree. So to start with, what are our actions? Well, we're flipping or rolling a die. And after that, we are going to select a ticket. So what are our outcomes for each of these? The first one, after planting our seed on the die, we could get one of two things. We could either get a bin A or a bin B. Then, once we're in bin A, we could select a ticket, either red or white, and we could do the same thing from bin B. They also have red and white tickets in there. And that's our tree diagram set up. We still need to put some values on there, though. So bin A, we've got 3 red and 2 white tickets. So 3 red, 2 white, a grand total of 5. In B, we have 4 red, 1 white, so still a total of 5 tickets there. And then when we go back to the die, it says there are 4 faces marked A, so 4 A's, and 2 faces marked B, and that would be a total of 6 faces. which is typical of a normal die. And now I think we've got everything set up here. The first question just says, find the probability the ticket is red. So if you look at the tree diagram, there's a sample space of 4 here. There's 4 different possibilities. A in red, A in white, B in red, B in white. And we are just focusing on the reds. So this is one red that we want, and here's the other red we want. We just multiply straight across, so we've got 12 over 30 for this red with the A, and then with the B, we have 8 over 30. To find the probability it's red, we combine those two ways to get red. We add 12 over 30 plus 8 over 30, which gives me 20 over 30, or 2/3. So that's sort of an old school tree diagram question. Now we get to the new part. The ticket was chosen from B, given that it's red. Well, when we have a tree diagram, we need to use that formula. So I'm going to write that formula down that we gave a couple slides ago. It says the probability of A given B is equal to the probability of A and B divided by the probability of B. Well, we do have A's and B's in this problem, but I'm not sure they're the A's and B's that they put in this sort of generic formula. So what I will often do is I'll write the whole formula again, but this time leave all the letters out. Keep all the symbols in. I've got my and symbol, all my parentheses, my given symbol and stuff, but now I'm leaving it blank. So it says the ticket was chosen for B given that it's red. So what were we given? Given red. If I look at this formula that I wrote here in the red ink, it says the probability of A given B. So in the original form we were given B, but in this problem we're given red. So I'm going to fill in place of my B's everything that is red. So probability here of something given that it's red. That's what this statement is saying now. Now I look back at the rest of the problem. It says the ticket was chosen from B. So in all my remaining spaces, I'm going to put a B in. So now this final formula here in blue and black says the probability of B given that it was red, or the probability that it came from B given that it was red, is equal to the probability of coming from B and being red divided by the probability of just being red. It seems like a lot, but really all we are doing is dividing two numbers. This number here, the probability of red, and this number here, which is the probability that it came from B and is red. And you'll actually notice that we already have all those things, so we just need to put it all together. So the probability of B given red is equal to the probability of B and red. Well, take a look at your tree diagram. B and red, right here. We already did that. It's 8 over 30. So that is my numerator, 8 over 30. We'll end up with a double-decker fraction here. And now just the probability of red, which was actually the part that we answered all the way back here in part 1, which is 20 over 30. We're essentially done. We just need to simplify. So how do we divide two fractions? Multiply the reciprocal. So you have 8 over 30 times the reciprocal, 30 over 20. Cross cancel, the 30s cancel out, leaving 8 over 20. And that would be the probability that the ticket was chosen from B, given that it's red. You may want to replay that one, try it on your own, and then you can also take a look at question number 3 on your own. The ticket was chosen from A, given that it is white. All right, from the book we have page 600, number 5 to 13 odd, and we will have a test on probability diagrams and combined events, not actually next class, but the following class. But at this point, we should be ready for that test. Until next time.